Hello and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. This involves collaboration between the universities of Bergen, Oslo, Tromsø, and NTNU, and working with Sigma 2 to manage the national e-infrastructure. In this video, we'll look into parallel computing on CPU cores, focusing on OpenMP, Open Multiprocessing. OpenMP aids developers in creating programs that leverage multiple cores for faster execution. It works with C, C++, and Fortran. By using OpenMP, writing parallel code becomes simpler and enhances performance on multi-core processors. We'll utilize the Fram Linux cluster for parallel computing using OpenMP, so let's log in to Fram. Upon logging in, we'll find a welcome message with helpful documentation and support information. Additionally, we'll see updates from the ops log and important notes and warnings. The Fram Linux cluster consists of 1,004 nodes, and Fram is the oldest Linux cluster in the national e-infrastructure. Each normal compute node houses two 16-core Intel Broadwell CPUs, giving a total of 32 CPU cores per node. These nodes are equipped with 64 gigabytes of memory. Additionally, there are 8 large memory nodes, each offering 512 gigabytes of memory. Since we've solely worked with the Saga Linux cluster, we need to transfer all our files to Fram. To start, we'll create a directory named mxm on Fram. Then, we'll use the Linux command scp secure copy to move files from the mxm directory on Saga to our new mxm directory on Fram. For additional details on file transfers, you can check out the onboarding videos available on this YouTube channel. These videos provide in-depth explanations and practical examples to help you understand the process better. We load the latest Intel Fortran compiler using our alias Intel. To see the modules loaded with this alias, simply use the command module list. Just a heads up, the Intel alias is set in my .bash rc file. It loads the Intel 2023B module and other modules, as seen with the module list command. On Fram, there are various job types available, and we'll opt for development jobs. These jobs can utilize up to 8 nodes with a maximum duration of 30 minutes, but for our task, we'll only need a single node. In our setup Python script, we request one node for our interactive development job without specifying memory usage. Since we're asking for the entire node, we automatically get access to all 32 cores and the node's memory. This gives us 64 gigabytes of memory to work with. However, the Linux system reserves some memory, leaving us with approximately 59 gigabytes usable. As a result, we can perform matrix multiplication with dimensions up to 32,768. When executing the Python setup script, we transition from the login node to the C8512 node. Using our CPU bill alias, we confirm that the billing factor is 32, matching our request for 32 cores. Furthermore, we note that we have 59 gigabytes of memory at our disposal. Before we begin any parallel computing, let's first identify the most suitable compilation options for a single core. We'll employ the same Python testing script used on the Saga Linux cluster, which relies on the OS and time modules. The file names remain unchanged from those used on the Saga Linux cluster, as we simply copied all files from Saga using the secure copy command. we'll test the Intel Fortran compiler using a matrix dimension of 8192 and calculate the number of floating point operations in gigaflops. We'll execute the program 3 times to calculate the mean wall time, just as we did on the Saga Linux cluster. We'll use the same compilation options as on the Saga Linux cluster, but this time, we'll specify the CPU to be of the Broadwell architecture type. The Python testing script will otherwise remain consistent with what we used on the Saga Linux cluster. When the Python testing script is executed on the C8512 compute node, it displays the complete compilation options. It's essential to ensure that both compilation and execution occur on the same compute nodes. Compiling on login nodes and executing on compute nodes can introduce unwanted discrepancies due to potential architectural differences. We observe that the inter-procedural optimization, IPO, yields a performance of approximately 16 gigaflops per second. By including the mat-mul option, we achieve a performance of around 44 gigaflops per second, which is similar to what we obtained on the Saga Linux cluster. Now, let's take a closer look at the matrix multiplication loop in the Fortran program. In our Fortran optimization video, we explored how the compiler achieves parallel computing on the innermost loop using the SIMD process and the AVX vector register. We can parallelize the outermost loop using OpenMP. So, we'll now implement parallel computing from both sides of the loops. When examining the matrix multiplication for all j and k, we can split this operation across the j loop into multiple calculations, a process known as multi-threading. As an example, we can assign one thread to handle calculations for j values between 1 and 8, while another thread tackles values between 9 and 16 and so forth. Each thread can run on a single CPU core, allowing us to utilize all 32 cores for 32 threads. In theory, this could accelerate the calculation by a factor of 32 compared to using only one core. The effectiveness of multi-threading depends on how many loops in the program can be divided into threads and processed simultaneously. If, for instance, 90% of the program's calculations can be parallelized with OpenMP, it suggests that a significant portion of the workload can be completed simultaneously. Given these assumptions, if we were to employ 2 threads, the theoretical speedup would be approximately 1.82. By increasing the number of threads from 2 to 4, we can achieve a theoretical speedup of around 1.69. Upon increasing the number of threads from 4 to 8, we can expect to observe a theoretical speedup of approximately 1.53. This is followed by a theoretical speedup of around 1.36 when progressing from 8 to 16 threads. Eventually, the theoretical speedup becomes about 1.22 when transitioning from 16 to 32 threads. This highlights that even with a considerable portion of the workload being parallelized, the speedup diminishes quickly with each doubling of threads. The remaining 10% of the workload, which cannot be parallelized, becomes a bottleneck for the parallel computing performance. You've already seen the Python testing script for executing on a single core, as we've applied it on Saga and now on Fram. Now, I'll introduce a Python script designed for testing with OpenMP. This script will also utilize the OS and time modules as the Python testing script. Additionally, we'll use the matplotlib and the numpy modules to plot the performance of the matrix multiplication with OpenMP. I've developed a Fortran program called mxm_openmp.f90 for matrix multiplication using OpenMP. We'll begin our testing by evaluating the performance with a matrix dimension of 8192. As we've done previously, we'll compute the number of floating point operations in terms of gigaflops. To obtain a reliable measurement, we'll execute the compiled Fortran program 3 times and calculate the mean wall time. We'll employ the thread numbers specified in the threading array. A single core test, denoted by threads equal to 1, serves as our baseline. For each thread number, we'll execute the test 3 times to determine the mean wall time. We'll utilize the compilation options previously tested on a single CPU core, along with the addition of the OpenMP compilation option. The variable doCompile holds the entire compilation command, which is then displayed in our terminal using the Python print command. Afterward, it is executed using the OS module. We're utilizing 5 distinct NumPy arrays, each containing the same number of elements as the threading array shown above. The variable index is employed to store values in the elements of the NumPy arrays, with its initial value set to the first element, which is 0 due to Python's zero-based indexing. The multi-threading loop consists of a double-nested structure. The outer loop provides the number of threads to employ, while the inner loop determines the number of times the program is executed to calculate the mean wall time. For our tests, we've opted to execute the program 3 times. The execution command, exe, specifies the number of threads that the program should use during execution, and this command is printed to our terminal using the Python print function. We utilize the variables start and end to measure the wall time for executing the program, with these variables obtaining their values from the time module. The execution command is carried out using the OS module. The variable wall timeout holds the text wall time, along with the value calculated by subtracting start from end to determine the wall time. The variable wall time sum is used to calculate the mean wall time, employing the method of cumulative summation. We calculate the mean wall time and mean CPU time. It's important to note that the CPU time is the wall time multiplied by the number of threads utilized during execution. The mean wall time and CPU time are stored in the NumPy arrays W time and C time respectively. We calculate the gigaflops based on both the wall time and the CPU time measurements. The NumPy array cores stores the number of threads used for execution, and then the index is incremented for the next execution where the number of threads is increased. The multi-threading loop concludes with printing the mean wall time and mean CPU time. Additionally, the performance in gigaflops is printed based on both the wall time and CPU time. We'll utilize the matplotlib module to plot the wall time and CPU time as functions of the number of threads used for execution. This figure is saved as a PNG file named time.png. PNG stands for Portable Network Graphics. It is a graphics file format that supports lossless data compression. PNG files are commonly used for images on websites because they support transparent backgrounds and provide high-quality graphics. We'll also utilize the matplotlib module to plot the performance in gigaflops as a function of the number of threads. Let's take a look at the Fortran program that will utilize OpenMP. In this program, we first load the OpenMP library or module employing the use instruction. As mentioned earlier, we'll begin our testing with a matrix dimension of 8192. We'll initially conduct testing without applying multi-threading in the initialization loop. We'll introduce multi-threading to the matrix multiplication loop. This is accomplished using OpenMP directives identified by a Fortran comment sign, followed by a $sign, and the letters OMP. Specifically, we're employing the parallel do directive, which splits the J loop into threads for concurrent processing. It's important to note that the compiler will execute a loop interchange, swapping the J loop to the outermost position and the I loop to the innermost. We'll save the actual testing for our next video, where we'll explore the performance of multi-threading in matrix multiplication. I am looking forward to the next video, wishing you all happy computing in the meantime.